All right, here we go. So today we're going to talk about inclined planes. A lot of this is again going to be review, but we're going to go a little more abstract here. We're going to leave a lot of numbers out this time, okay? So we're going to be learning about inclined planes. For now, we're going to just assume no friction. In one of the next couple of videos here, we'll add friction in, okay? So, simple examples. Suppose you've got an inclined plane, and a box is placed on the plane, and let's suppose it's inclined at 30 degrees, all right? Let's make a free body diagram and find the acceleration, okay? So what forces are acting on this thing? Well, there's gravity that's pulling down, right? So here's our force of gravity pulling down. And there's got to be some sort of normal force, all right? We know that our normal force has to act perpendicular to our surface, right? And I think that's it, right? So what we learned last year was this. And I even talked about this in video 4.1, was this idea that we need to choose a coordinate system such that our acceleration will be along one of our axes, right? And so what we do is, instead of using the standard x and y planes, I said that backwards as I drew it, but you know what I mean. Instead of using those two coordinates, what we do is we rotate them so that we have a parallel axis that is parallel to the direction of motion and a perpendicular axis, right? But what that means then is my normal force lies along the normal axis, my normal force lies along the perpendicular axis, but gravity doesn't, right? So what we're going to end up having to do is we're going to have to take that force of gravity and split it up into components. One that is along the perpendicular axis and one that is along the parallel axis, okay? So let me not draw that quite so fat. So what we end up with is this force of gravity and this force of gravity. So this guy is our perpendicular component. This side here is our parallel component, and the hypotenuse is our FG, right? Notice this is our right angle, okay? Now, it turns out, I'm not going to go through the geometry, but it turns out that this angle here, the angle at which your ramp is inclined, is the same as this angle here, right? It is totally worth your while to convince yourself of that, okay? To make sure you understand that, all right? And so what that ends up resulting in is this. It turns out that your, excuse me, your parallel component of gravity is just Fg times the sine of theta, because your parallel side is opposite from your angle. It's the opposite side, right? And similarly, Fg perpendicular depends on the cosine of the angle, because the Fg perpendicular is the side that's adjacent to the angle. Okay? So, with that in mind, let's do this. I'm going to clean up my drawing here. All right, so again, just to be clear, the technical free body diagram is this, right? As I said in that first video, when you make a technical free body diagram, you don't draw the components, you draw the actual forces, okay? But it doesn't help us at all in terms of problem solving, right? So, to make our problem solving free body diagram, what I'm going to do is this. I'm going to replace my force of gravity with the two components. All right. So the parallel component of gravity will always pull down the hill, and the perpendicular component of gravity will always push into the hill, or pull into the hill, I guess I should say. All right. And then there's a normal force. All right. Now, I know that these two forces are equal, right? They have to be, because our net force in the perpendicular plane has to be zero, because the box isn't going to move either into or off of the ramp, right? So let's write down the values of these. So this Fg perpendicular is just going to be Fg times the cosine of theta, right? And Fg is just mg, right? Mass times 9.8 cosine theta, and it's in a negative direction, right? So that means my normal force must be positive m times g times cosine of theta. So those guys cancel out. All right. So now we're just left with this guy, which is m mg, and our parallel component is sine theta, mg sine theta, right? Sorry, I skipped a step there. Fg is the same as m times g, right? Right, and it's pulling in a negative direction, right? Okay, so now what we do is the infamous net force equals net force. Okay, net force, Newton's second law tells us that net force is mass times acceleration. Okay. We know that our normal force and our perpendicular components cancel out, so it's really just equal to Fg parallel, right? So we get MA equals negative mg sine theta. Divide both sides by m, and we discover that the acceleration of a thing on a frictionless inclined plane is just negative 9.8 times the sine of the angle. And for us, our angle is 30 degrees, so you want negative 9.8 times the sine of 30 gives you negative 4.9 meters per second squared, okay? All right, so but the big takeaway here is on an inclined plane with no friction, there's your acceleration, negative g times sine of theta. As a quick reminder, I don't know if this is maybe throwing anybody off, but just real quick, remember ag is always negative 9.8, and then g is understood to be positive 9.8. Okay, so we had to kind of manufacture that negative by putting that in there, okay? All right, so there's that. I guess if you don't trust me, there's the answer. Okay. Okay. Okay, cool. So let's do another example. All right, so now it says, write an expression to determine the force needed to push the box up the ramp with an acceleration of a. Assume the force is parallel to the ramp, okay? So here's our ramp. It's inclined at some angle, theta. Here's the box. Here is the always amusing force of u. And our goal is we want the acceleration to be a, right? So let's do this. So other forces we know we have to deal with are mg, that's the perpendicular one, right? So that's cosine of theta. Over here we've got mg sine of theta, negative style. This one should be negative. You've also got a normal force, which is positive mg cosine theta. I guess I should label these. This is my FG perpendicular, and this is my FG parallel. Okay, so I think that's it. Those are all of my forces. And I should say that in this one, it's fairly obvious that the force of u had to be directed up the hill. If you didn't know that, the next step would reveal that information to us. All right. The other thing that we know is we want our acceleration to be a up the ramp, right? Okay, and we want to write an expression for the force of u. All right, so we're going to start out the same way we always do in these problems. Net force equals net force. So the net force on the object has to be the mass times the acceleration. Our net force in this problem is simply the force of u plus Fg parallel. So mass times acceleration is Fu plus negative mg sine theta. So I think we can add the mg to both sides, and you get Fu equals ma plus mg sine theta. If you want to simplify it further, you don't have to, but just if you want, this becomes m times a plus g sine theta. All right. Notice here our acceleration is positive because we wanted it to go up the ramp. If we wanted it to accelerate down the ramp with that acceleration like this, then we would have to say, oh, well, that means this acceleration's got to be negative. So you'd have to put a little negative sign there, right? Okay. Assuming that a represents the magnitude of the acceleration, right? But basically, you just need to make sure that this whole value here, this negative a is in fact a negative value. Okay? So that's how you do that. All right, let's do one other thing here. All right, this one says, write an expression to determine the force needed to push the box up the ramp with an acceleration of A. This time it says, assume the force is parallel to the horizontal. Make a complete free body diagram, okay? Oh, do you know what I didn't do on this last one was I didn't make my technical free body diagram. I guess I should do that real fast. Oops, try that again. So the technical free body diagram of this would be this. Here's your ramp, here's your block, here's your force of gravity, here's the force of U, here's your normal force. And I guess as long as I'm being technical, really this whole thing should be represented as a dot. Okay? All right, so moving on. Now, so this time we got the same goal, but this time we want our force to be not parallel to the ramp, but parallel to the horizontal. So you still got your ramp inclined at an angle of theta, but this time you've got gravity pulling down. You're going to have your normal force. And this time, here's your force of U. Okay? Oh, shoot, I did a rotten job drawing that force, didn't I? No. Oh, darn it. Try again. F, N, F, U. Okay? So now the problem becomes this. We've now got two forces, oops. We've now got two forces that don't lie along either of the two axes, okay? But because our acceleration is this way, we have to stick with our parallel and perpendicular axes, okay? So here is what we need to do. We need to split up our vectors, okay? So here are my axes, parallel, perpendicular. All right, so here's our FG. All right, remember we did a little bit of geometry that shows us this angle is the same as this angle. I don't know why I'm rederiving this, but I've come this far, I'm going to finish it. So here's theta. So that means that FG perpendicular is FG cosine theta, and FG parallel is FG sine theta, right? Okay, so that we already knew. That's review. Okay. Now, what about FU? So here's my parallel axis. Here's my perpendicular axis. Here's my, darn it, I wanted that to be black, and I failed. Here's my FU, right? So I guess the thing to notice here is, remember, this angle here is theta, right? That means that this angle here is theta. So I want to draw a triangle that includes that. So what you end up with is FU parallel and FU perpendicular. Here's my right angle. Okay? So now, let's see. If this is my angle, that means FU perpendicular is the opposite side. So FU perpendicular here turns out to be FU times the sine of theta. And similarly, your parallel one uses cosine. Okay? So, my point here is you got to be careful. When you're dealing with an inclined plane, vertical forces, how do I want to say this? Your vertical forces have a perpendicular component that depends on the cosine of theta and a parallel component that depends on the sine of theta. But that's only true for a vertical force, okay? Whereas if you've got a horizontal force, then your perpendicular component depends on the sine of the angle, and your parallel component depends on the cosine of the angle. Okay, and that's only for a horizontal force, right? And then if the force is at some weird angle, you know, like if you had Roy pushing, you know, like this or something, then it gets even more complicated, okay? And it does happen. Okay, so I'm going to pause for a minute and let's consolidate all this stuff. All right, so here we go. So all I did was I kind of took everything and smooshed it onto one page. So let's see if we can make a free body diagram with all of our components. So here's my ramp, here's my box. What forces are there? Well, there's normal force, FG, and FU. So our FG, we're going to replace with these two guys, right? So there's FG parallel, which is the same as, I'm going to write this, mg cosine of theta. Darn it. Hang on. Thank you for being patient. Not that you have a choice. Okay, here we go. So FG parallel is negative mg cosine of theta. Okay, so that's that. We've got our FG perpendicular, which is negative mg cosine of theta. This one over here should have been sine of theta. Sorry about that. All right, cool. So that's my force of gravity that I just poorly dealt with, right? Okay, cool. So that's that. Now we've also got the force from U, the two components of that, right? So part of the force of U accomplishes getting this thing to go up the hill. That's the parallel component, so that's FU times the parallel one uses cosine. Right? And then there's another part, this part over here is sort of pushing into the ramp, right? So there's also FU perpendicular, which is FU times the sine of theta, right? And then finally, we've got a normal force. So our normal force needs to be big enough to ensure that our up and down forces cancel. So we've got, vertically, we've got two, I say up and down. We need to ensure that our perpendicular forces cancel. In other words, this normal force needs to cancel this and this, right? So our normal force here is going to simply be big enough to cancel out positive mg cosine theta and positive fy sine theta. So it's mg cosine theta plus fu times the sine of theta, right? Okay, so there's our free body our free body diagram with components, right? Remember, this is the technical one over here with no components. All right, so we're almost done. So now the last thing is we got to do net force equals net force. Right? So let's see, net force. Our net force should be the mass of the box times the acceleration. That's got to equal Fu parallel plus Fg parallel. So Ma equals negative equals Fu cosine of theta minus Mg sine of theta. So let's see, we can add, so we get Fu times the cosine of theta equals Ma plus Mg sine theta. And then divide both sides by cosine of theta. So Fu ends up being Ma plus Mg sine theta, which is the same as what we had before, divided by the cosine of theta. All right? Very abstract. Lots of algebra. All right, there you go. Inclined planes. You're welcome.